Hello, everyone. Welcome to Essence VC's Q1 virtual conference on LLM Inference. We're happy to have you here. We have a great lineup. And just so you can know who everyone is, I'm Naomi Walker. I'm the head of platform at Essence VC. We focus on the early stage and technical founders that are building in data infrastructure and dev tools. We like to host these quarterly conferences so that we can jump in and go deeper on topics that are top of mind, where there's a lot of advancements, and that we want to share what our Essence founders, as well as our greater community of researchers and founders, are working on. Sorry for starting a few minutes late, but we are very excited to jump into things. So without further ado, I'm going to bring Zhang to the stage. He is going to chat through a lot of what he's been working on in his lab. He's the assistant professor at UC San Diego. He also he's a co-founder of LMNet AI, and he is a maintainer of vLLM. So he's going to share more about what he's been working on. Let me bring him to the stage.
Okay, yeah, let me share my screen. Okay, just want to make sure everyone can see, right? Okay,
Good.
cool. Yeah, let's get started. Yeah, DQ, sorry, I think we switch order. Thank you, team, and thank you, Naomi, for introduction, and thank you, Ethan, for this great opportunity for me to talk about our latest development in the vLLM community, or in the general LLM inference community. Yeah, let's get started. We only have 15 minutes. Okay, we all know LLM, right? It's now the biggest thing, and it can enable so many interesting and fancy applications. And apparently, GPU is one of the most important resources, and we just passed, actually, I should not pass at GTC, right? And GPU is the essential resources to make sure LLM can run. But the GPUs are very expensive, and hence, in the LLM inference world, I think all LLM service and endpoint providers, they want to minimize the cost of serving LLMs, because that will directly translate into lower dollar per query, which will again make a higher margin for profits, and which is the key for the success of many business. Okay. But in order to minimize the cost per query, the most popular LLM serving engines today all focus on improving a metric which we call throughput. And this includes almost all libraries that you can actually enumerate, including vLLM like Hugging Face, DeepSpeed, NVIDIA, and many others. And they basically optimize this throughput. And this throughput basically measures how many requests or tokens you can serve per second, given a fixed amount of GPUs. And as you can see, in our original vLLM blog post, when we released this last year in June, we also compare with TGI using this metric called throughput as a major measure. And there's nothing wrong about this throughput, but it leads us to ask the question, is throughput really a good enough measure considering the rich diversity of LLM application and service today? And in this talk, I'm going to talk about, I'm going to give a slightly different message, okay? So besides throughput, many LLM applications are often offered as a service provided to users, like very similar to any internet services. And therefore, for such services, we do have some equally important metrics, which we usually call service level objectives, right? SLO. And in LLMs, there are generally two most important service level objectives, okay, which I put it here. We call it the TTFT and TPOT. And the TTFT stands for time to first token, and TPOT stands for time per output token. And I'm going to explain these two terms, okay, using examples. So for example, a chatbot needs to have a relatively fast initial response, or time to first token, in order to make sure the user experience is good. But after that, the following generated text doesn't have to be faster than average human reading speed. This means that the TPOT, which is the time per output token, after the initial token generation doesn't have to be too fast. You can still make a satisfied user experience. Okay. And very differently, users who use a summarization application can tolerate a longer initial response time because it doesn't matter like when it will return the first word, right? But we want to see the summary as soon as possible. That means that the subsequent generation should be fast. Okay. And this example basically give you a sense like what does this TTFT and TPOT stand for. And then the question is, in the presence of these two service level objectives, TTFT and TPOT, like, should we reconsider throughput? Like, is throughput a sufficiently good measure for ARM serving systems? We want to ask this question. And it turns out that this is not always the case. Like, throughput is not always a good metric. Like, suppose we have a system that can serve 10 requests per second, as shown in this figure, where the x-axis is the time and the y-axis is the request we serve. And we basically also illustrate the TTFT and TPOT we achieve. And as you can see, if we are able to serve 10 requests per second, we are good. At least it's good for today's systems. But when we pose an actual constraint on TTFT and TPOT, we see that only 3 requests survived under this criteria. And which also means that this is 3x less requests that we can serve without breaking the SL. Okay, so basically we can call this portion of throughput that is subject to listening constraints. We can give it a new name, which is called good put. Okay, and this term good put actually reminds you of some old networking research and development where people optimize the packet delivery or video streaming quality, right? They also have a very similar metric good put, and we basically reuse that word. And ARM serving indeed shares some similar ideas here. Okay, so and in this case, we can see that the core message I want to give is a high throughput does not always mean high good put. But good put is actually the one metric that is associated with your user experience in your service. So this leads us to ask an important question. So why do existing systems fail to achieve high good put? Yeah, let's take a step back and understand how a request goes through this LLM. Okay, so when one request comes into an LLM inference engine, it usually takes this kind of process. I actually made some visuals here. So the system will take the user input to generate the first token. And this process is called prefill. I think everyone probably are very familiar with this process. And once we start prefill, we generate the first token, right? And we continue this process. And after prefill, the request starts to generate the rest of the text token by token until it finishes like this. And we call this process decode. And a request usually consists of one prefill step, but multiple decoding steps until it terminates like this. Here we terminate because we hit the EOS unknown sequence token. And once we finish the decode, the request will leave the system. Okay, this is the general illustration of the LLM inference process. Actually, I made a GIF here, but the point I want to make is like in all typical LLM serving systems or in all today's serving systems, we usually batch the prefill and decoding requests together using a technique which is called continuous batching. I think this continuous batching is a pretty fancy word, and I think any skill published a very nice blog post to discuss why continuous batching is so powerful. And continuous batching allows us to batch multiple requests together for one iteration, so it can effectively enhance the overall throughput. And this technique is widely adopted in popular serving systems such as vLLM, TRT, and all like today's systems. However, the two phases, prefill and decode, they actually have very distinct characteristics in computation. So here I want to illustrate these characteristics. So prefill is very compute bound, meaning that a small batch of prefill or even a single long enough prefill will soon saturate the GPU computation like flops. It will use up all the flops. On the other hand, decoding needs a much bigger batch size to hit the compute bound, and is more easily subject to memory bandwidth limit of GPU. Okay, this means that their computation characteristics are very different. But because continuous batching co-locates prefill and decode, so the two phases actually interfere with each other. And I actually draw a visualization to show this kind of interference on this slide. So on the left figure, we basically batch two requests, R1 and R2, together in one GPU. And we can see that in the red window, actually the pink window, when R2, which is a request 2, arrives, R1's decode is batched together with this prefill, R2's prefill. And R1's decode time, which is in blue, get significantly delayed because of R2's prefill. And similarly, R2's prefill time, which is in green, also get slightly increased. But on the right hand, I can show a contrast figure. Because we separated these two requests, R1 and R2, into two different GPUs, like they are basically working in two different phases. They actually don't have any interference, as you can see. Okay. And this is even worse when the system receives an incoming stream of requests. Like suppose we look at the figure on the right. Now the request in the decode phase gets significantly delayed every single time when a new request comes into the system. As you can see, R2's prefill interferes with R1's decode. And when R3 arrives, R3 interferes with R1 and R2. And when R4 comes, it will interfere with all affinity requests in the previous arrival. You basically get the idea, right? Okay. As a result of this interference, when services must satisfy both TTFT, time to first token, and TPOT, time for output token SLOs, basically we have to provision more resources to meet the latency goal, especially when either SLO is strict, as you can see from this figure. On the left, we don't have 3 requests meeting SLO, but in order to make sure that both LLs are met, we have to basically squeeze the bar by adding more GPUs. Here we increase the number of GPUs from 1 to 4. And apparently we have to suffer a higher cost, right? And there's one more problem I want to highlight with this co-location. That is the paradigm strategy we used are inherently coupled for the prefill and decoding computation. So basically remember that the prefill and decode has very different computational patterns, and different applications also have different latency goals for a TTFT or TPOT. And because of this, the optimal parallel strategy for prefill and decoding phases should be different. But in this case, when we put prefill and decoding together, we actually cannot uncouple their parallelism. For example, when TTFT is tight and TPOT is loose, the prefill phase actually prefers using some sort of a tensor parallelism to meet the tight latency target, where the decoding phase prefers data or pipeline parallelism to actually boost the throughput and reduce cost. And if we co-locate the prefill and decode, we don't have a choice to configure parallel strategy for them separately. Okay. To summarize, co-location causes 2 major problems. One is that the interference between prefill and decoding caused by continuous batching. Second is basically their parallel strategy is coupled. Okay, that is one of the most important problem I want to highlight during this 15 minutes talk. And then I'm going to use the rest of time to briefly illustrate the idea how we solve this. So is there a better way to achieve better output here? Indeed, there is. Actually, the solution is pretty simple. We just need to disaggregate the prefill and decode into 2 different GPUs. And in this slide, I basically altered my previous visual into from a co-located system into a disaggregated system. And by looking at this visual, I think you can quickly grasp the idea. And as you can see from this animation, the request first goes into the prefill worker to finish prefill. And then we migrate the computation from the prefill worker to decoding worker. And this migration, it sounds very expensive, right? Actually, we can prove it's not expensive at all. It starts decoding until it finishes the generation and leaves the system from the decoding worker. That is basically a very simple idea. Let's see a concrete example why this simple strategy would give us improvement. And this is the real profile we run on vLLM actually. But I simplified it into 2 very straightforward plots. So basically in this plot, on the left hand, you can see the x-axis is the rate. We are gradually increasing the request rate going into the system, where the y-axis is basically the P90 TTFT and P90 TTOP. It's basically latency, okay? And we can see as we increase the rate, apparently the system will need to suffer more traffic, so the latency will grow up, right? And we can see from the upper figure that the system can support roughly 3 requests per second that stay within the TTFT latency constraint using one GPU, right? We just need to set the latency goal. Here I set it as 400 milliseconds, and then I draw a vertical line and project to the x-axis. I see the rate is 3. And similarly for the TP-OT, it can sustain the 1.6 requests per second. So therefore, the overall system output is just the minimum of these two, which is 1.6 requests per second. Because for each request, we need to serve its prefill and decode, right? Until we can claim it's finished. But if we disaggregate, things get significantly better. So if you look at the right part of this figure, so first, because we are free from interference, we can observe that both the green and the blue curves get somehow flattened compared to left. This is because when we disaggregate these two phases, we basically eliminate the interference. Now each GPU only need to take care of one type of task, either prefill or decode, but not both. As you can see, the prefill can achieve a 5.6 requests per second, and the decode can basically achieve a 10 requests per second, which is stay within the constraint. Okay. And more importantly, now we have the flexibility to allocate different GPUs for prefill and decode. Here we simply allocate 2 prefill workers to pair with 1 decode workers. We call it a 2P1D. And with 3 GPUs in total, we can basically get a 10 requests per second for the whole system that is stay within latency constraints. And if we average over all GPUs, we basically get a 3.3 requests per second per GPU. And if you compare this number to the left, which means that our average GPU throughput is at least twice, okay? And this is a very simple strategy that gives us 2x throughput per GPU speed up. And we can actually make this way more complex and more optimized by actually optimizing the different parameter strategies that we're going to implement for prevent decoding. And we can actually gain more. And if you are curious, please feel free to check out our paper. I will share this slide. But here I basically give you a high-level idea why like disaggregating prevent and decode can give you way better performance. Okay. With this idea, we actually implement some initial prototype on top of the vLLM, and we evaluated against the vanilla, the current vLLM. We tested our system on 3 different workloads and datasets, and each of them has distinct latency constraints. And as you can see from the slide, our results show consistent throughput gain ranging from 2x to 4.5x. And I'm not going to over-index on this in this talk because we have limited time, but feel free to check out our results. Okay. To summarize, I want to summarize the talk. So to summarize, we're actively integrating this as a major feature update to vLLM. We are going to optimize throughput instead of throughput because today people, I think they emphasize latency a lot. And disaggregation is basically effective to optimize throughput. And as you can see, the number is pretty good. And we are integrating this into vLLM open source. And if you are a current vLLM user, you will basically see this pretty soon. And there are already some internal versions being adopted by different companies. Okay, that's pretty much all my talk. And thanks for attending. Yeah.
Thanks so much, Hal. That's really great. I know it's a lot to get through in 15 minutes. And everyone, friendly reminder that please, just because we have a designated Q&A session at the end to talk about broader questions, don't hesitate to type in questions to the Q&A function on the webinar, as speakers can try to speak to them as they're sharing as well. We had to have a last minute change to order, but we're kind of going back to the intended order now, and presenting TQ Chen, who's the co-founder and CTO or chief technologist at OctoML. Let me bring him to the stage.
Okay, great. Can everybody hear me? Yes?
Yes.
Yeah, thanks for the introduction. So hi, everyone. You can call me DQ. So I'm a assistant professor at CMU as well as a co-founder chief technologist at OctoAI. So today I'm going to tell you a bit about our recent work on universally deploying large language models. So, I think a lot of people have motivated, why we need to be able to do fast inference and deploy more language models, right? But the question is that, can we go one step further in general? Like right now, if you look at state of world, most it look like the left-hand side, right? You get, users, you send your data to the cloud, most of the system optimized for one kind of hardware backend. But in general, can we make it even more accessible by enabling a broader wave of hardware support, as well as will you be able to bring into a paradigm where you have some models that can run locally together that interacts with something that runs on the cloud. So personally, I'm really excited about how we can move our future towards that goal and make some of that happen. But in general, that will pose a lot more challenges, since effectively our goal here is, hey, you get a language model, can we deploy universally? That means that it runs on your phone, your laptop, bigger models still runs on cloud. Effectively, then can they collaborate with each other? But the real issue here is software. Software is always the issue. We get hardware that have necessary compute, but just to give an example, if I want to deploy, say, my models onto some consumer devices, and if you just count the number of GPU runtimes you have on those consumer devices, at least there are 9 of them. And that means that you have to kind of build software for 9 of them, and that's only GPU runtime. But even you have the same GPU runtime, building something for, say, a Qualcomm device versus another device that supports OpenCL is very different. Okay, so how do we do that? It's kind of engineering problem, right? So ideally, typically what you do is you try to build specialized library stacks for each of the hardware backends. Each vendors have their own teams. Some of them have different resources. So you can say, usually there are certain stacks that are far ahead of others. And one of the questions we're thinking about is, can we try to automate that a bit more? And specifically, more recently, you have seen works in PyTorch and other ecosystems starting to look into this field called machine learning compilation, which also I'm actively working on. Actually, we started this field about 4 years ago, and it's starting getting more tractions. The goal here is you want to be able to take high-level machine learning models, you bring them onto what we call a high-level ML abstraction that represents what kind of computations you can do in those models, and then you start to do what we call composable optimizations that hopefully can be reused. A lot can be reused across hardware backends. And these optimization include things like operator fusions. You want to plan your memory so that they run more efficiently on a local code, and then you have ways to dispatch to effective libraries and so on. So specifically, what we build is we are building on top of this compiler abstraction called Apache TVM that allows you to be able to represent high-level machine learning programs, machine learning kernels in that contains elements like dynamic shapes that's kind of essential for supporting effective language models. And with that program abstraction, we can start to ingest models from existing libraries if necessary, start to transform them, and also be able to export to any of the hardware backends. And so if you have a module that captures the kind of computation you have in a machine learning model, what you do is you will be able to export it onto kind of environments that the runtime supports. So the environments will include, of course, the Python environment. You will be able to load it onto an environment that don't have Python. You will also be able to put it on something like a web browser directly through JavaScript. Okay. And the goal here is not necessarily, one thing that you might observe is that I think I would predict is that a lot of developments nowadays is not only going to be about algorithm developments. A lot of them are going to be about, system optimizing innovations and how do you continuously optimize your machine learning system. And in order to do that, we kind of need a way to be able to, continuously improve your pipeline of optimizations. In this case, in a lot of cases, you might want to be able to start to change your own libraries depending on for implementing things like attention, be able to try out different fusion strategies, and be able to quickly bring that back onto your optimization pipeline for a certain hardware backend. So to specialize that for language models, so we have developed this framework called MLCLM that allows you to be able to take in existing language models, try to build up a collection of common optimization patterns and deploy them onto different kind of runtime backends we have out there. So in terms of development patterns, if you look at a normal development pattern, assuming a framework foundation, it looks like a left-hand side where you try to change your function ordering and compositions to make it faster. If you have done compiler development, you will find that usually you are working on a backend. But in a lot of things nowadays, we kind of need to work on both the front end and back end to be able to really get the best of the system. Okay, so that's like the high level, and then I'm going to talk about some of the things that works in real action. And so first of all, we will be able to directly bringing in those models onto local computers on MacBooks that generalizes to even 40 billion. That's a work starting, I think earlier this year, and still, we're working on some of this. We will be able to fit those models onto phones. So if you go to your app store and search for MLC Chat, you will be able to download this app. Latest apps come with Mistral and Phi support. So we'll be able to take the same model and doing quantization and bring it down onto your mobile phones directly. And this is running in real time. Okay. Of course, it also comes with Android support. This case is running on a Snapdragon with OpenCL backend. And of course, we also love different kind of GPU vendors and backends. So we have also looked into, can we directly take the ML models and swatch our backend, in this case, trying out AMD. And we can find that actually, with our approach, we can quickly bring some of the solutions to be competitive. And actually, as a matter of fact, we spent about maybe a few days to be able to 1 day to make it work, and a few days to get the performance to be decent, and which looks really promising. Okay. There's also interesting question on how cheap you can go. So one thing that we can enable is you can bring these models onto this $100 Orange Pi board that have an OpenCL backend. You can run, I think, 3 billion model pretty fast, and a 7 billion model in a decent way, like 2.6 tokens. It's not really usable, but 3 billion model, I think, is usable. And considering it's $100 board, it's kind of interesting. Okay. And finally, if you want to try out one thing today, I would just encourage you to go and try this out. So go to webm.mlc.ai. And if you have a laptop with usually with web GPU enabled, if like usually Apple laptop will suffice, you will be able to start interacting with the chat demo that directly runs inside your browser. So it's not sending any data to any of the servers. What's happening is that as you first go to this web page, it will download the model weights cache in the browser, and then it leverages the technological web GPU that allows you to leverage your local GPUs and run the language models. So web GPU just ships in Google this year, and Google Chrome this year. So effectively, if you're interested in building our AI applications on top, we also have an NPM package that we can directly use to build a local version of the language model directly in browser. Of course, it also comes with a good amount of server support recently, and we are doing a major revamp of the MLCRM, so of the Universal Deployment Engine. The project started about a year ago, and we are getting to a mature stage so that we can support, overall surfing support across all the backends, full OpenAI compatibilities and more modalities. So there are exciting things coming soon. With that, I would like to also talk about OctoAI. So effectively, a lot of the technologies that we're building here powers the OctoAI engine. And we are, in this case, we are trying to deliver good API endpoint that allows you to be able to efficiently do things like text gen, image gen, all the other stuffs very effectively. And if you're interested in related area, another thing I would like to mention is that MLC's conference is happening this year at Santa Clara in May, and we have awesome line of speakers. It's a venue that contains a lot of relevant papers to set up language model systems, and a great community that do research and works around the topic of machine learning system, which I believe is increasingly very important nowadays, considering all these advances and system requirement here. Okay, with that, I would like to conclude the talk, and I think we are early, so which is fine. I think. Okay, thank you.
Thank you, TQ. Yes, all right. So I'm running a little bit ahead of schedule, but we're going to be bringing on our next speaker, who is Daniel Lenton. He's founder and CEO of Unify. He's going to share a bit. You may know him from Ivy, but he's going to share a bit about Unify's new model hub on how dynamically routing prompts, different language models can improve the performance cost profile over any individual model on coding tasks. So let me bring him to the stage to share more.
Amazing. Well, thank you very much for the very kind introduction. So let me just get my tab sharing on, so hopefully you can see my screen. Yeah, okay, so yeah, well, first of all, really great to see so many people in the audience. A real honor to present in front of all of you today. So today I'm going to be going through our work on how to get the best LLM on every prompt. So first of all, just a little bit of context. As we all know, the AI landscape is really booming. There's explosive growth, not only in lots of new models, but lots of new layers of the stack effectively. There is a whole new layer where people are building on top of language models. There's things like, LangChain, Llama Index, and chain of thought reasoning and so on. So a really exciting time for AI, and the number of models just continues to increase over time. Yeah, the way that I see it is that we're effectively entering this endpoint era. There's a lot of companies that were conventionally working on more infrastructure areas, OctoML being a great example. Now obviously getting involved in doing really great work on LLM endpoints and Stable Diffusion endpoints and so on, similar with Anyscale and Neural Magic and Grok even now with their own endpoints as well. So there's really a lot of companies entering the space with their own verticalized AI as a service offerings, mainly in LLMs, but also obviously in text to image and several others as well. So yeah, very exciting time for the field. One of the things that we're very interested in is just the fact that, particularly with so many different models and serverless GPU and orchestration layers and compression techniques and compilers and hardware, there is really a lot going on, a lot of different ways of deploying models, and there is no one shoe fits all when it comes to the optimum way of deploying it. So some applications require low cost, others require low latency or high accuracy or high throughput or low memory, and these things are all in direct competition with one another, and it's really not obvious how you can get all of these at once. So the first observation that we've made is that basically what people are typically doing is that they are choosing an LLM. Let's focus on LLMs for now, and most people are choosing one model and one provider and sticking with it. And it would look something like this, and you're sending all your queries to this model with this provider. And that's great. Obviously, it generally works. The only downside with that is that then you're effectively, if the provider suddenly has a lull in performance or it goes down a bit, you are kind of locked in and you're going to ride the performance waves of that given provider. So one thing you can do here is that, let's say you know what model you want to use, let's say Mixtral, and what you can do is say, well, I just want to have the fastest at all times. I want the lowest inter-token latency based on the latest available data in my region of the world, and I don't mind how that's being achieved. I just want it to be as cheap as possible, and that's where you can do effectively dynamic routing with one model and then routing across several providers. And in terms of the benefit this can unlock, so you can imagine that basically through time you have some variation in performance. There's some kind of macro trends in terms of performance that's available. This data actually is quite old, but this is kind of also hypothetical data about what you would see going through time with some of these providers. What you can then do is effectively do an argmax, where instead of riding the peaks and troughs of one provider, you can effectively just have the fastest or the cheapest at all points in time. Of course, things like cost change less often, but they do still change quite often, obviously with it being quite a price competitive market. So even if you just don't want to try to keep up to date with which is the lowest in terms of tokens per second, or input tokens per second, output tokens per second, you can just kind of sacrifice, let us deal with that basically, and we'll kind of make sure to always bring the cheapest or the fastest or whatever it is you care about. So I can get very quickly just to quickly show what that looks like. Let me very quickly share my screen for a moment and just kind of show you basically what these runtime results look like. So we have in this case Mixtral 8 7B instruct. We can change the region from Hong Kong, Belgium, Iowa. We can do short sequence length, long sequence length. All of this is explained in the benchmarks page. We can have a linear scale or a log scale. We can do averaging over the last 5, or just look at the latest data. And we have results from several providers together: Octo, Replicate, Mistral, Perplexity, Anyscale, Fireworks, Lepton, Dmytro, and Bedrock for now. But Vertex AI and Grok and several others are fast in the pipeline to get them added. And you can change output token per second, time to first token, etc. And there's some really interesting things you can start to see, even just like, let's take Mixtral, for example, and look at the provider Mistral. So if we're in Belgium, and we look at time to first token, we actually see that generally speaking, Mistral is the fastest. Maybe not surprising, their servers are based in Europe, most likely based in Paris. So if you're working from Europe and you really care about responsivity, probably you should go with Mistral for this model. However, if you're in Iowa, probably should go with Fireworks, because obviously, I guess the servers are far away and you have, got to travel across the sea. So just some of these kind of things are the kind of data that pops out when you start to have this multi-region perspective and a time series perspective on the runtime data. You can also then go query any of these endpoints and so on, and get single sign-on and everything basically. So that's just kind of a very quick demo of what you can do with our open runtime dashboards. But getting back to the deck, so here we go. So that's all well and good, and you can get some nice performance improvements in terms of runtime and cost as well. But things get really interesting when you start to take a broader perspective, which is, well, what if we don't only route across different providers of the same model, but what if we route across different models and different providers? And this is something, there's obviously been some early research on this in the last few weeks in particular, but the intuition being, what if, should you be sending questions like, what is the capital of Egypt to GPT-4? Probably not, because Llama 7B knows the answer to this, and it's a fraction of the cost. Really hard things should go to the expensive, difficult models, but when you have easier parts in the prompt space of your task, they should go to cheaper models, because you can get just as good quality at a tiny fraction of the cost. And this is the intuition behind dynamic prompt routing, and you're optimizing this joint function of cost, speed, and quality. So diving into, we've been doing some experiments here. So the first question is, can we create a model which is, so we basically, we're doing lots of experiments. I've decided to keep things reining in 50 minutes. I'm going to focus the talk on, one simple experiment just to get the concept across, basically. So the question is, can we create a model which is cheaper than GPT-4 while it's being better at coding than DeepSeek, which itself is much cheaper than GPT-4? So first of all, we plot these two data points. We have GPT-4, in this case, assumed with Oracle knowledge, that's $30 per million tokens. And then we have DeepSeek, which based on the Glaive dataset, which is 140,000 examples, based on the Glaive dataset, DeepSeek is correct about 80% of the time, based on GPT-4 as an oracle. So we have the GPT-4 point at the top, we have DeepSeek at the bottom. Can we train a router that is, as I say, better than DeepSeek, but cheaper than GPT-4? So the first thing to say is, well, what is the upper bound? What is the best router that we can possibly imagine? And this is what we represent with this router oracle at the top left. Basically, you can imagine what we do here is we take a look at the response from DeepSeek. We see, is it good enough? Is it correct based on GPT-4? And if it is correct, we assume that we routed to DeepSeek correctly, assuming that GPT-4 as an oracle is correct. And if we routed to DeepSeek every time it was correct, we would have a router, we would have a system that is as good as coding at GPT-4, just as good at coding as GPT-4, but less than $10 per million tokens, so much cheaper. And this is kind of the upper bound for this particular task that we can strive for. Now, the first thing is there is a trivial solution here. A really obvious thing you can do is just say, well, 50% of the time I'll go to GPT-4, 50% of the time I'll go to DeepSeek, and you would expect to basically have something along this interpolation. So if you always go to GPT-4, you get this point. If you always go to DeepSeek, you get this lower point. If you go 50-50, the expectation of performance will be along this interpolation line, basically. So the question is, well, can we do better than a trivial interpolation? And can we learn something about when DeepSeek is better than, is good enough to answer this question? And the answer is, I actually intended originally to have these things appearing one at a time, but didn't quite get the time. So it's all been there on the whole slide. But basically, yes, we can. This is just a neural network that's predicted to take in the prompt and say, can DeepSeek answer this question or not? So we don't need to actually query DeepSeek to know. And across different batch sizes, we are getting a bit of better performance, but we are, the interesting thing is how can we push all the way up there? And we're doing some interesting experiments at the moment to kind of push performance even further. But the answer is, as a kind of initial starting experiment, yes, we can. We can get a router that, for example, if we use this neural function, we're getting half the price of GPT-4 at about 98% of 98% accuracy of GPT-4. So you can learn with a simple approach a routing function that gets some way towards the upper bound that's theoretically possible. So now some other questions that we've been exploring is, well, what does this mean in terms of the data sets? Are some languages harder to learn? Again, this is based on the Glaive 140,000 data set. Are some harder to learn or some easier to learn? And what we've seen with some early experience is that Java is a bit easy to learn. We're a bit closer to the Oracle on Java. Python, somewhere between. One that's really hard is assembly and Rust, partly because they're smaller amounts in the data set. So, I mean, Python is 25%, Java's 9%, SQL's 9%, assembly and Rust are both smaller percentages. So it's yet to be seen whether these problems are just so fundamentally difficult or whether it's because of a data problem. But there are differences in terms of the performance you can get on certain languages, and a very interesting area to be exploring as well. So just with a quick example of getting the routing done correctly versus incorrectly. So basically, routing across models. In this case, the question was, can you provide a Python function that receives a list of strings as input and returns a dictionary with the frequency counts of each word? The answer from DeepSeek, in this case where we correctly routed to DeepSeek, was sure, here's a Python function that does exactly that. And basically, I mean, you can read through it yourself. The function works by iterating over each word in the input list. If the word is already in the dictionary, increments the count for that word. If it's not, it adds the word to the dictionary with a count of 1. So relatively simple function. And in this case, we were correct for the router to say, yes, DeepSeek can do this. No need to waste money on GPT-4. However, there are still some issues where we don't get it right. So in this case, there was a question, how can I rearrange? Oh, someone's editing the slides behind the scenes with me as well, which is why things are moving. Can I rearrange a given array of Python such that the first element is the greatest and the second element is the smallest? And they give an answer here. Yeah, so the second element of the returned array is the second smallest, not the smallest. So basically, it was not able to get this one correct. Just 2 cherry-picked examples. Just I'm not sure what we can read into this massively than to say that there are things that there's still routing decisions that it's not able to learn. But certainly it's able to learn something beyond the the trivial interpolation, basically. I think that the kind of general future directions, there's a lot of things we're really excited about here. So while at the moment the focus is very much on routing across open endpoints of these models, basically there is interesting enterprise potentials here. One of which being, can you take a load of fine-tuned models, a load of open source fine-tuned models, do fine-tuning on each of those open source models on the local data set, start to get some disambiguation in the prompt space, so that each of these open source models, let's say Gemma 7b, Gemma 13b, Mixtral, etc., all of these models, do they start to specialize in some way? Do they start to specialize it in some way where then certain areas of the prompt space are better, more appropriate for other ones, and then you also fine-tune a routing function as well, jointly with the fine-tuning of the small models, and then you end up getting something that's more effective than a single massive open source model that's just been fine-tuned on the data once with LoRa, and you have a smaller mixture of experts, I suppose, given that Mixtral itself is a mixture of experts and so on. So that's a very interesting direction we're working on with some companies at the moment. And last point is just that we're looking at future directions, one of which is we're very excited about. We've already done some early experiments routing across different modalities. So inside text-to-speech, text-to-image, text-to-video, there's some really interesting routing work that can be done. There's routing work that can be done across these modalities, so sending it in a general request, and this can then be sent to different models based on the prompt. So a lot of really interesting stuff, basically. And that is it. Yeah, hopefully that was okay on time. Thank you very much for listening, everybody. Oh, but the questions are at the end, so don't ask your questions yet. But yeah, thank you very much for having me. I guess, yeah, Naomi.
I'm jumping back in. All right.
Sure.
Thank you so much, Daniel. All righty. Okay, so we next have Dmytro Dzhulgakov. He also goes by Dima. He's the CTO of Fireworks AI and one of PyTorch's core maintainers. He's going to talk to us about approaches to customize LLM inference for specific application use cases to deliver the best speed and quality. So I will bring him to the stage.
Yeah. Hi, everyone. Thanks, Naomi, for the introduction. So yeah, my name is Dima, and I'm going to talk a little bit about opportunities of co-designing LLM inference in applications. So first, I want to talk a little bit about OctoAI and what we do. So we are a Gen AI platform, which primarily focuses on delivering the best quality and speed for open weights models. We believe that control of people's destiny should be in their hands. So using open source models and fine-tuning on them is the path there. And we pride ourselves in being as fast and affordable. So I think Daniel was showing just now some benchmarks from Unify Hub. So we're happy to be there on many graphs on top. We support a lot of like all the best open source models, obviously LLMs, but also across modalities like image, video, and various combinations thereof. And our previous background has been in like myself included in like building PyTorch. So we are very developer obsessed. So our goal is to make sure that it's easy to implement these APIs and leverage LLMs in applications across some of the features which I'm gonna talk about today. So to start, I mean, like why are we actually even talking about LLM inference? Why we have this conference? Isn't it so simple? You have some runtime, you get your model, you basically talk to it in English, you give it a prompt, gives you the output, nice and simple. You can API is pretty simple. You can integrate it in your application. Turns out, if many application use cases, you actually need to go deeper than that if you want to get the best speed and the best quality. And opportunities here, I kind of group them in two categories, both of which what people call this co-design opportunities, which is basically the ability to jointly optimize use case and particular LLM inference, LLM model implementation. On one side, there's a whole bunch of hardware optimizations, which I think TQ touched upon earlier, like how to parallelize scale, how to go low precisions. We've done a lot of work there, which you can check out, like for example, FP8 inference and stuff like that, or even how to craft the model architecture to be more hardware friendly. But there is also another side, which is how to suit requirements of applications and how learning about particular pattern of how the application uses LLM allows to craft a better solution for that. So we've been doing a lot of this with a lot of developers and customers over the past year or so. So in this talk, I want to primarily focus on the examples of this kind of LLM inference engine and application co-design. So I'm going to touch on a few of them and see how they're being used in Firefox inference platform. To start, I mean, one trend which been kind of going on quite a while, which was actually a surprise for us, like after starting to run it to the platform, is that prompts keep getting longer, and there are two primary reasons for that. One is multi-turn chat, right? People love to have lengthy conversations in many cases, even if they have few turns. There are usually huge systems prompts with a few short examples, etc. If you add function calling kind of interaction with tools, it gets even crazier with longer arguments. And obviously there is a RAG where you would retrieval augmented generation, where you would take a lot of documents and try to stuff them in the context of the model. So even though like in common benchmarking, people usually look at like 3-to-1 ratio of like how long the prompt is compared to generation. In reality, like in many use cases, this is like a sample of use cases we looked at on our platform. Many of them actually fall into a ratio of like 10-to-1 or 20-to-1, where you have like this really gigantic prompts, but relatively short generations. And actually a lot of work in kind of LLM inference has been on optimizing just the generation portion of it, which means that we can do much better on the prompt processing side. So one insight there is that those prompts actually repeat quite a bit. So if you look at multi-turn chats, then all the previous conversations keep getting included every time you kind of send in this next message. Same happens with function calling, or if you do kind of like iterative code rewriting for Copilot, for example, there's the same context which keeps repeating on every request. And actually, like you could basically build support engine where you can take the previously pre-computed key value caches for the previous requests, keep them around, and like reuse them when the next request arrives. You don't need to reprocess the whole prompt once again. Another example where it happens is that for cases where you're trying to do RAG, or where, for example, you're trying to in many techniques, like for example, like split, answer, merge, kind of chain of thoughts reasoning, right? You often, for example, start with like a single document, but have multiple questions, multiple kind of aspects to evaluate it on, which you want to run against the document, for example, multiple queries against the document, run them separately, and then I have separate LLM call to summarize them together. That's like another example where like crafting how you do the prompt. How you use the prompt, you can lower the latency and make the speed much better. For example, by putting in this case, by putting the document first and appending different queries to it, subsequent requests end up being like multiple times faster, just because you don't have to reprocess the very long prompt. But for example, for this like demo we had initially, like taking the really long like Tesla urgent summary, you can like answer repeated queries for it much faster just by issuing those requests, and by baking it into the inference engine, you can basically make it transparent to the colors of your API. Interesting thing is that in principle you can actually generalize this work to kind of more generic RAG. If you do RAG naively, you kind of concatenate all the documents together. So later documents do attend to the earlier ones. I think there is an interesting space of research kind of on how to tweak attention mechanism and how to customize it. So basically, in ideal case, if you have a documents database, you could actually pre-compute kind of LLM outputs for those documents and just recombine them based on the query only for the documents which are relevant to this context, which seems pretty exciting as a kind of generalization of this idea. Another kind of aspect which helps clone prompts, and conveniently how I actually had this talk just before covering this, so I go very briefly, but an interesting observation that many real-world constraint use cases, there are pretty tight latency constraints. So if you want to, in order to match them, and how I was calling good foot, you need to actually underload your GPUs to match those that latency requirements, which means much higher cost. This is especially true for long prompts, because long prompts can go and have GPU for a long time, basically jeopardizing latency for other requests. By disaggregating or like by pulling them out, processing of prompts into separate GPUs and kind of balancing this depending on the use case, you can get quite a bit of improvement. So this technique, I mean, how I had a talk like implementation is deserved. I think there are some with earlier papers about similar techniques. We also had it in production for a while, so it's actually helps quite a bit in real-time use cases, which is pretty exciting. And again, it's pretty transparent, like doesn't require any API changes for the end developer. Putting all of this together, we actually see that in many cases by combining these techniques and some of the other ones and crafting the deployment properties just for specific traffic pattern for the application, you can get holding the same latency constraints and holding the same requirements. You can get often like 3x higher throughput or even more, which basically means 3x lower latency for particular use cases. And we've been working on this and there kind of dedicated deployments, customers to help them do that. Another aspect which is pretty exciting for LLM inference is speculative decoding. So you might have heard about this technique, but the core idea bases on the fact that LLMs are autoregressive, so they actually generate one token at a time, and this generation is often memory bound, which means an interesting counterintuitive property. It's actually about as fast to process multiple tokens in parallel for LLM, for example, during prompt, or if you somehow can do verification during generation, as it is to run just a single token. So the idea of speculation bases on the fact that can we have like some kind of small drop model which can guess what tokens the main model will generate, and then just main model just to verify whether they're correct or not. You can think of it as, you know, senior and junior engineer analogy. Junior engineer is fast but does a lot of mistakes. Senior engineer is always correct but slower, and you're basically asking the like junior engineer and intern to like write a bunch of code and have the senior engineer just go and review it in one go, which takes less time than writing all that code by hand by the senior guy. So speculative decoding is fascinating because that's actually like the speed of processing the request now depends on the content of the like what this request is about. For example, if you ask LLM, this LLM engine is speculative decoding turned on to do something simple, like count to 100 or something, it's gonna run much faster than if you ask it to generate some creative text, where the smaller model will have harder job predicting what's gonna happen. And that actually makes benchmarking sometimes harder. But this is also something which we can exploit for many real use cases, because many of them are pretty narrow and specialized to a particular domain, right? You might be talking only about financial information, or maybe like be some personal assistant or some customer chatbot. So even if you're using the really large capable of LLM, like the text you're generating falls in a small category. Also, in many use cases, models actually just recite input. Like if you're asking compiler to rewrite something or summarize text, like the same phrases from the input appear pretty much verbatim in the output. So you can kind of customize how you do speculation based on that. So the key, example of co-designing this application, like what if we can actually take, customize how these drafts are generated based on particular use case, just by looking what inputs and outputs flow to the system. Nice thing that even though you are training the model, you don't need any additional data, because your inference system is producing this data already. So you can do it basically shipped in automatically. And we've been experimenting with this with some of the dedicated deployments, and actually see like pretty nice, like 50% or even 2x speed ups for use cases which generate more structured and narrow domain data, kind of benefiting from this quite a bit. Another area where I think interaction with applications means a lot is interfacing the structured data. And if you've been following kind of LLM space, you know that this is function calling and JSON generation has been a really hot thing. The core idea is that you can ask your LLM to basically output structured information, for example, some JSON data structure or some particular DSL, to interface with your broader system. For example, go take some actions, call APIs, fetch external information, etc. There is a question of how to LLMs tend to hallucinate. So how we can guarantee that it actually produces good output. Like historically, people started just with prompt engineering. You like operate a tip or threaten to kill a kitten or something if it doesn't comply to generate a particular JSON output. But turns out you can integrate it into the runtime, and there have been many approaches to do it. But basically, you are forcing the output structure for LLM, like every time it picks the next token, just to generate tokens which are valid for this position. For example, if it's like a field in particular JSON object, only choose from one of those fields. If it's like a number, only generate digits, which actually helps to patch a lot of issues, but does not help by like it's not ideal by itself. So you also want to focus on much higher quality models, so even like fine-tuning them on particular structure, which can be done often effectively using synthetic data, and can be done pre-training generically, but also with focus on particular use cases. And the question is like which structure you want to say. Like as we started building ways of expressing structure at Ferris, and you start with like something simple and just ask model to produce any valid JSON and add some kind of schema to it. For example, saying like, hey, object with these fields, etc. What we found is that JSON sometimes is not even the best format for many use cases. It's kind of hard to handle. It's very verbose, has always like string escaping, which is annoying. So we kind of moved to the next stage of flexibility by allowing people to basically specify arbitrary grammar, so a combination regex and kind of context-free grammar description, which many people kind of took and kind of built interesting approaches upon. I think this idea originally started from Llama CP, but that's a pretty flexible approach, which gets enables a lot of use cases. And of course, you can imagine even further customization, but by basically writing custom parser for a use case. I think there was some work from Microsoft kind of suggesting that, but it's a little bit crazy, maybe hard for a lot of developers to grasp. So how we leverage these techniques at Fireworks. First of all, there is like the structure generations integrated in runtime. So you get pretty much no overhead and still 200 tokens per second speeds, even if you use structure generation. As I said, we do support custom grammar, which I think we're one of the only API providers offering this support. Like as a great example, people used it for example, forcing only particular character sets or banning some subsets of output formats, like as a flexible developer tooling. And we also focus on kind of building specialized models for structured outputs and function calling. For example, we released an open source like Fire Function, which is our fine-tune of mixture called Llama, which particularly focuses on generating structured output and extracting intent. Often can match kind of GPT per level at fraction of the cost and speed, which allows you to build pretty exciting kind of experiences with that. But you can apply this technique for pretty much any base model. And final aspect which I want to look at is kind of model customization, basically fine-tuning. Again, if you follow LLM space, there's been explosion of interest in fine-tuning techniques, in particularly in LoRa. Why is it useful? Is it offers you more control and often can push quality higher than what is possible with prompt engineering in future of examples. It also ends up being cheaper because you can grab a smaller model and often get to the same way with higher quality, and you don't need to send those huge prompts every time. And with kind of LoRa as a particular technique, it's been actually very approachable to train models either on your own or on kind of on hosted solutions. So it's basically accessible and it's very quick to iterate for a particular use case. But what is needed kind of from the platform like inference runtime to manage those like hundreds or maybe thousands of models effectively? So one observation is that like, the good thing about all these API providers, Fireworks included, and OctoAI, etc., is that there is serverless inference, right? So if you just call in GPT or Mixtral or whatever, you don't need to pay for GPUs sitting out there. You can send requests on demand and just pay per token. If you do naively with fine-tuning, that doesn't work because nobody is going to be willing to host your model, which gets very little traffic, but sits resident in GPU all the time. You can get pretty far with auto scaling, and I think Erik's model, we're going to talk about some of the stuff, which is an interesting approach. But specifically for LoRa, you can do a different trick, which again I think been valorized in some open source projects. We also had it for a while in our system, which is effectively cross-model batching. So the idea is that since LoRa changes on the small set of parameters, you can kind of load them in memory in the same GPU as a base model. And when a request arrives for a particular LoRa adapter, you just kind of on the fly route only part of you still have a bigger batch, but only like that part which touches the LoRa parameters gets executed against a specialized adapter, depending on which kind of model variant this particular request was sent against. That effectively allows you to pull kind of all the traffic to the same small number of GPUs, have high compute efficiency and effectively lower cost. And what we kind of been building with Fireworks is a kind of combination of platform which leverages both sides of this. So we provide fine-tuning service, which makes it really easy to kind of grab best open source models, take your data, and kind of start fine-tuning without managing kind of infra complexity of figuring out what the right recipe is, and transition to serverless inference for your fine-tuned models. So you get the same top spins. You still pay absolutely the same price as a base model. You pay per token only. And what it enables is really like from developer perspective is this fast iteration loop where you can like fine-tune in minutes, immediately evaluate, and learn what works and doesn't work in your application, repeat and iterate quickly without kind of having to provision infrastructure and manage all those details along the way. So wrapping up, we looked at in this talk I can touch on several opportunities of how to exploit particular patterns of how LLMs are used in the wild to enhance LLM inference engine. We look at some of those today. There's much more which we also develop, kind of which are power Fireworks AI behind the scenes. So also if you want to try it for fast and flexible inference, give it a try. Our developer platform is over there too. And with that, I'm done with this talk, and thank you. I guess we're doing questions at the end, so please file down there.
Thank you, Dmytro. That was great. I love the senior versus junior engineer metaphor there. Okay, as a reminder to anyone who joined later, we actually had Hal join First, so the order is a little out of order from what you're seeing on the wallpaper screen. So we're going to actually move to our final speaker session before our Q&A panel, which is with Erik Bernhardsson. He is the founder and CEO of Modal, and he's going to provide us a more technical breakdown of how companies like Suno using Modal Labs to scale inference, batch pre-processing to thousands of GPUs, and more. So I'll let me move the spotlight over to you, Erik, and I'll let you take things away.
Hi, thanks for hosting me, Naomi. Yes, I'm the CEO of a company called Modal. We're based in New York. We build data infrastructure for data, AI, and machine learning teams, focused on, in particular, a lot of inference. Some of our customers run quite large deployments of several thousands of GPUs running various types of GPU-based inference models. So it's a lot of, for instance, like one example is Suno, like you just mentioned, Naomi, which does AI-generated music. We also have a fair amount of like LLM companies using us for LLM fine-tuning and LLM inference. But our focus is more to be like kind of a general purpose platform for running code. We're not like an LLM engine per se. You can run LLM engines inside a Modal. So let me share my screen real quick. I have a couple of slides. So real quick, with Modal, you can run any code in the cloud. Like we basically take your code, execute it in the cloud, scale it up and down as needed, run it on GPUs, like whatever. And then in the sense, you know, we're essentially a function as a service platform in the sense that we run the code and then we charge you based on the time it takes. So let me quickly share my screen, another screen, and I'll show you real quick, like very basic example of like how you can use Modal. And then I might show like one or two things also around like LLMs specifically. But I wanted to start by showing some like very basic, just like what is Modal to start with. Sorry, I opened the wrong file. So here's a very, very simple example of how to use Modal. So Modal is both the Python SDK and the infrastructure to run containers and in production. So in this Python SDK, the idea is you can just actually take any function in Python and turn it into a cloud function in just a few lines. And this is a very sort of trivial example. All we're doing in this function is to print some stuff to send it out and return a square of a number. So if we run this thing, basically we have to like we basically take your code, move it to the cloud, execute it in the cloud. When it's printing, it streams back. So the idea is like you almost have like a workflow that feels like you're developing locally, even though you're executing in the cloud. And this extends to, let's say we want to like, you know, edit the code or and like run something else. Like you don't have to like build a Docker container and push it to the cloud and go trigger something in a console and download logs. You have the ability to basically like work with this code almost as if it's locally. And also, you know, doing things like, let's say we want to run this on H100. So, you know, let's allocate on H100 for this. And we'll see how that goes. So now we're basically firing up a container on an H100. And it's like this just execute on H100. Modal also has built in, like you can define like custom container environments. You can give us a Docker file. That's one way to do it, but you can also do it in code. So let's say we want to install some stuff. We can basically do it in code like this. Pip install, say we want to install LangChain. Then I can say image equals image and run this thing. And now we're going to build a container in the cloud and we can, whoops, sorry. I don't know what happened. Maybe LangChain is not let's install Annoy, which is a vector database I once built. We'll build these containers in the cloud. We can build containers extremely quickly. We cache these with the second time you run it. And so the idea is like you can, you know, you get the power of Docker without having to deal with Docker. In fact, we don't even use Docker. We built our own container builder, built our own file system, built our own scheduler. We built a lot of the infrastructure that's needed to run serverless containers. And because you can start these containers so quickly, you can also do sort of bursty parallelism, like kind of fan out things. So let's say I want to run this thing. Well, let's do it on an A10 because we have a lot more availability of those. Let's say we want to fan out and run like 1,000 containers or at least a few hundred containers. You can do basically something like this in code. we can map over these functions. So square.map, we can map over 1,000 elements. If you run this thing, now it's going to fire up several hundred containers running with 810 GPUs. And in each one of those, I guess it's still printing. Oops, did I like? Oh, it's printing two things. It's printing the square. That's why it's confusing. So the idea with this is like you can do this like bursty parallelism. And like I mentioned, you can run almost anything in Modal. So like one example is something that quite a lot of companies do with Modal. Ramp is a good example, for instance, is do LLM fine-tuning. So we have an example repo. I'll share a link too of how to kick off a fine-tuning job. You can basically run axolotl inside Modal. So here's one example where we're fine-tuning Mistral based on SQL instruction pairs. So we're kicking this off and we're running it on a multi-GPU H100. As you can see, we can fire up two GPU H100s very quickly. As you can see here, I don't know if it's easy to see, but yeah, we're running on two H100s in production in the cloud. And now it's kicking off this fine-tuning job. Takes a few minutes to finish. And the nice thing is it's all in code. So if you want to, you can kick off lots of fine-tuning jobs in parallel. You can sort of fan out and kick off, programmatically 100 fine-tuning jobs or whatever. And then once it's fine-tuned, it dumps an adapter to our file system, and it's pretty easy. There's some code examples for how to then run inference on that. It takes a little bit of time, so I'm not going to do it here, but I prepared some slides just to show you what that looks like. If I'm able to share the screen here. So here's the link, by the way, to the repo if you're interested. This basically provides some like scaffold code around like axolotl in Modal. It's just a few hundred lines. Basically, just like 100 lines of Modal code to get axolotl running in Modal. Yeah, the like why using Modal for fine tuning? Like again, like Modal is like a general purpose container platform focused on compute intensive jobs. It's not an API for fine tuning. You actually have exact control over what code that's running. So whatever you want to do with the code, like if you want to use structured output for the inference, if you want to mess around with hyperparameters, if you want to do a grid search, we find that quite a lot of companies end up starting out with some API provider in the cloud, like just like Fireworks or OpenAI. But often, there's a point where many companies end up, realizing they want more control, either for just want more control of like particular parameter. In some cases, they want to use custom workflows, custom code. In some cases, it's more around like they want to fine tune a much smaller model, like distilling a model that's smaller. So there's a cost component of that. Or in some cases, some people are just like nervous about, running things in OpenAI and sharing potentially data with OpenAI. So there's a lot of reasons why customers often come to us for doing their own fine tuning. And then once they're doing fine tuning, obviously doing inference. So I mentioned Ramp, for instance. Ramp is a customer here in New York also. They use Modal to extract, they fine tune a model based on receipt data, and then they use Modal, or they use then the LLM, the fine tuned LLM to extract structured data and basically JSON from this receipts when you upload like a receipt. And Modal makes it super easy to deploy an inference endpoint. You can get both sort of, function that you can just call a Python function from another context, or you can, sorry, I don't know if I have an example, but you can deploy a web endpoint. So you can basically curl that or hit it from some other language and do LLM inference, streaming or batch or whatever. In fact, like one example, one common thing that people use Modal for is like we have this ability to do this very bursty parallelism, right? So you can fan out and get hundreds of GPUs crunching your data. Here's a very simple example where we're just like mapping over like translation tasks. It's a very chatty model, so it varies a little bit what it actually responds with. Embeddings is another example that a bunch of customers use it for, and we have a blog post on how to take all of Wikipedia and fire up vLLM and embed, create a vector for every Wikipedia document in about 15 minutes. And I think about $1 of cost or something like that, because it's all pretty fast, maybe a couple bucks, I don't know exactly the number. But this is another like benefit of using Modal. You have this ability to get very high throughput. We're not rate limiting you in the same way as a provider like OpenAI would. We can basically just like create more GPUs, and those GPUs like we can fire up like very quickly, as you saw in the example. Yeah, here's like another fun example. We built this little open source repo that basically interacts with the Slack API. It downloads all your Slack history and then creates like a clone of yourself that you can talk to over Slack. Another use case for that people often use Modal for in the context of LLMs is to run the agent on Modal. So even if you're using some sort of open source or some sort of external API provider for the LLM itself, it's often nice to have a place to deploy agents, like simple agents. And in particular, like small developer was an example of that, which is something Swix built that got quite a lot of stars. And then finally, like another cool thing where we spent a bunch of time on is the ability to run code safely. And this is useful specifically for code generation LLMs. So we have a primitive within Modal where you can take any code or any container and like execute that and like observe the output and interact with that container while containing the code, which is obviously useful if there's some sort of risk that code might be bad or be malicious in any way. Like you want to contain that execution environment, right? And so Modal has a concept called sandboxes, which lets you execute arbitrary code. And that's quite useful if you have an LLM generating arbitrary code. You can sort of stick it into the sandbox and execute it and make sure that sandbox doesn't interact. So we have a couple of examples of this as well. Yeah, cool. That's all I got. Quick demo. And there's a couple of chat questions. So I see some. I don't know if like Naomi is like now the time to respond to those, or should we progress to the next step?
We're about to jump into the Q&A session, so we can just start off with these questions. Let me pull everyone else into this so that we can have Tim kind of kick this off for us. So, Tim, I think you need to put on your, there we go. Okay, everyone welcome Tim Chen, who's the GP of Essence. He also co-hosts the Open Source Startup podcast. He has a rich developer and founder background himself, and he is going to kick off an open Q&A panel where we can answer some of the questions that are already filtered through, add more if you have more, and then I know he has some questions in mind as well.
Yeah, thanks, Naomi, and super appreciative and thankful for Naomi to organize and run this. This is not an easy task, so cool. Okay, so I have questions on my own, but I want to have everybody that's still here. I appreciate that. If you have any questions, put in the Q&A or put in anywhere chats, and we want to leverage this opportunity to chat about inference. I had the idea I want to do this because inference is moving fast, in this space. LLM is moving fast right now. So here's a ton of questions. Let's get into it. And, I'm going to run this pretty openly. It's a panel, but, we're also all friends. I think we know each other for the most part. We're gonna jump in one into another. And so I'm going to kick off a question. I know it probably a few ones, and I'm gonna let the audience to start putting up more questions in the Q&A at the same time. So hopefully we get more stuff going. All right. So, based on all the chatter today, one thing I got out of it is even though we all know we need GPUs, we're inferencing on top of LLMs, but actually what everyone is doing in this space is quite different, right? And everyone is actually focusing on different layers of the stack. So I think one particular question to start off with is, what do you believe is going to be the most commoditized parts of this inference stack that everybody will basically do mostly the same? And what are the parts you think are the most differentiated or most like valuable? And since you already hinted during the chat, but maybe even to be more specific, what do you think is the most important parts of this inference when you provide to your users? And let's go one by one. I guess Erik, do you have anything you want to start with?
I think it's roughly a function of two things. I ask myself, by the way, the same question like all the time, right? And like one thought I have in general about startups is, like who's actually a rapper versus who's like, have real technical depth. And that I think is like one big part of it is like, just like what's like, a real moat, like what's like, and in particular, like what's like real technical differentiation. The other thing I would say is like, what are the switching costs? So, you know, if there might be two startups that both have, you know, incredibly deep technical depth to them, but if the switching cost is very low, they might still find themselves in like a tough spot, you know, competitively. So I don't know exactly, you know, where it is. Like I'm obviously extremely biased. Like I tend to think, you know, Modal has both like, you know, high switching costs as well as like, you know, real technical comparative advantage. I don't have like a strong point of view of like, you know, other parts of the stack, like, you know, what's going to be commoditized in the long run versus what's going to be has like sustainable, durable business model.
Got it. But switching costs sounds like is, right? Like, how do you actually design your product to be, you know, as deeply ingrained in people's like integration? So that's, I assume, that's part of it. Yeah, Dima, do you have any thoughts here, or?
Yeah, I mean, that's a great question. Yeah, as Erik mentioned, like I think everybody here thinks about it all the time. So I think like I mean, I touched a little bit about in my talk. I think like the pure, like, if I don't know anything about use case and I'm running on the same hardware and I just want to give the answers situation, like, I mean, that's a pretty constrained problem until it is getting commoditized eventually. I think the opportunity lies either, you know, going down on hardware level and like hardware keeps evolving and kind of there's always moving target there, or going up towards applications which have mostly attached in this in the stock. Because I think we are just scratching the surface on like understanding end-to-end use case and applications. You know, you can squash last 5% of efficiency from like optimizing particular, you know, how you do matrix multiplication without knowing anything else, or you can look at kind of end-to-end use case and through combination of like modeling and inference engine and maybe like even some product development, figure out like, hey, how can we maybe not, you know, call a smaller model or leverage particular traffic pattern or leverage lower free use or kind of combine RAG and inference more efficiently, etc. Ideas like that, which potentially have, you know, like multiple X improvements both on quality and cost. And I think that's where it's much less constrained problem. So you'll see like more differentiation based on use case vertical and like different strategies which people take. So that's what I'm particularly excited about. That said, I mean, the base layer still has a lot of interesting things to build. So that's exciting too.
Yeah, that's super good point, actually. There's a lot of like specific things with specific use cases you can actually drive inference towards to. That makes actually quite a lot of difference. So hey, Hao, anything on your side? I know you do a lot of research. You're actually doing a company, as far as I can tell, too, right? So what's the thought process here of you showing your differentiation in this space?
Yeah, I actually agree with Erik. I think it's a switching cost, and maybe I can be a little bit more concrete. That is, like assuming LLM Inference will soon become free, then where can you actually add that switching cost for your users, right? I can think in that way. One of my thought is like by calling on the user actually is generating a lot of synthetic data, and I feel this synthetic data is actually something that will persist and very valuable to the users. And if you can draw values for the users for those synthetic data, probably that will be a switching cost. Yeah. So basically, my argument is I feel we can gradually transfer from this like inference service into like data business, and you know, data business has been very successful, like Databricks and Snowflake. Yeah.
Interesting. Yeah, that's a good way to think about it too. Yeah. Well, hey, Daniel, give us your thoughts in the taxi ride. What's your differentiation? We just be on the move and sell customers constantly. Maybe that's the answer.
Exactly. Yeah, it's got to hustle all day. Exactly. Hopefully you can hear me fine. Yeah, I guess one thing that I don't know, but one thing I can imagine happening is that there's maybe increasing specialization on the LLMs themselves. If kind of Claude 3 and GPT-4 and Gemini kind of reach some baseline ability on the kind of general jack of all trades models, that there's going to be like data moats, and there's going to be moats from kind of having access to maybe very good data sets for particular verticals, and LLMs could become more vertical specific and expertise, and that would then kind of maybe lead to kind of not like kind of almost a mixture of experts available in the open domain, and they could kind of stay differentiated accordingly with the quality of the LLM. The other thing in general, I mean, quite obvious, but obviously one way that people try to increase switching costs is by moving into things like fine tuning, where you then have your data set available in your account. So I think kind of one of the things that makes GPT-4 and OpenAI more sticky in general is moving away from just having GPT-4 as an API, moving towards my GPTs and having kind of in the browser, in the account, kind of customized models and stuff that then locks your data into the account. So I think probably kind of it's quite hard to, I guess like it's quite hard to remain sticky as a pure inference engine if you're not kind of operating on some level of customization as well, is kind of my thinking. But yeah, but I agree with everything else people have said as well. These are just some additional thoughts that kind of come to mind. Yeah.
Cool. All right, we'll go reverse order here. My last question here, and we're gonna get into the audience questions way quickly. What are you most excited about? In this inference space in the next year or two? Because there's so much stuff happening around. There's obviously multimodal. There's new techniques. They're getting smaller models. There's new non-transformer architectures. There's just a crazy amount of stuff that's just happening all the places, right? So, what is like the most exciting thing you think will actually be that's it better even maybe it's a little bit non-obvious too. You think will be actually change this landscape around inference? So Daniel, any thoughts or?
Yeah, well, I mean, I guess things will keep driving down and you're going to be able to do insanely more compute like exponentially. I mean, obviously, I've forgotten the name of it now, but like NVIDIA's new device that was announced a couple of days ago is like 30 times more powerful than the Grace Hopper one, for example. So I don't know, obviously Sora, I guess probably the high level thing is that I think aside from just doing like chain of thought reasoning with LLMs and so on, probably the fact that we can now start to go into other domains, just a high level, is what I think is most interesting for this year and the year ahead. Sora is obviously a very good example of what happens when you apply the same, data and compute scaling and a simple transformer to image, to video. So I just think we're going to see a lot more amazing video generation stuff in particular, where the scaling really starts to show what's possible. And I wouldn't be surprised if by the end of this year, you can write a prompt that says, generate me a 3-minute rock music video in the style of noughties pop punk, and you just have like a perfect video with audio, high definition. Like, I don't know, I just think the content creation is going to be crazy when it comes to videos. And at some point, I imagine in our like next few years, you can write a script for a movie. You can just take a manuscript for a movie and you're going to have the whole HD movie 2 hours long. Like, I think this is going to happen. So this is the stuff that I think is really exciting. Yeah.
Cool. How about you, Ha?
Yeah, I agree with Daniel. I think video generation is very interesting. I probably will speak from a technical perspective. For example, I did some estimation. For example, if you want to generate a one minute video, basically your contact length is 1 million. Okay, you start from 1 million, and that's your starting point. That's kind of crazy, right? Because it will break all the existing systems. Yeah. The second point, like I'm particularly interested, is like how you can make LLM's output more controllable. I think Dmytro actually mentioned a few efforts that they did in Fireworks, like structure output. But you can think LLM as a component in software engineering. Like in the past 40 years, why Silicon Valley can build so many like big infrastructure? It's because you can verify your output, right, at each layer of your abstraction. And if you try to replace the original like software engineering effort with LLMs, you also hopefully want to control the output of your LLMs. But apparently now LLM is more perform like a stochastic parrot, like most people said, right? And it's largely not controllable. So I feel we probably want to design some language or like tricks to make sure like we can layer it up on LLMs as the infrastructure. Yeah.
Cool. Hey, Dima, what do you think?
I mean, to add to, I think video as a domain hasn't been fully solved yet. So Sora is an interesting spark in that direction. So that there's definitely a lot more there. I think like as an extension of that, I'm like generally AI-wise, I'm pretty excited about like robotics applications, because like besides video models, like actually having like world models with kind of physical sensors, I think would be the next wave. I mean, specifically for LLMs, because we're talking about LLMs here. I think I touched about it a little bit. Is like to add a kind of controllability part, I feel like also a lot of pipelines and chains which people build today are kind of like ad hoc and try to combine things just from like passing the prompts and crafting English language. I mean, like RAG is an example of that, where you kind of bundle together multiple components, hoping it works. So I think there's like, if you extrapolate the deep learning trend, I think there is probably better solutions for that to be able to train and kind of optimize end to end. And you kind of see sparse pieces of this in some of the research, but ideally, like you'd be able to figure out how to like customize end to end more grounded system in like some existing available data, which is like faster than pre-training and more controllable, but also like higher quality than just like hacking and massaging the prompts, hoping that it works better. So I think, and that's the intersection of a lot of just optimization techniques and different attention mechanisms and system optimizations. I think that space is generally like pretty exciting.
Very cool. I guess Erik, you're next.
Well, no one mentioned like the hardware stuff, which I feel like should be mentioned, right? Like besides the GPU stuff, like I think it's fascinating what people are doing, with FPGAs or whatever Groks use, like Grok with the Q.
ASICs, yeah.
I'm not a hardware person, but to me that's like obviously like somewhat like LM will go down into that layer, and there will be like super customized like specialized hardware for like particular models where like the model weights are like burned into the hardware, and by doing that you can get much more energy efficient, higher throughput, lower latency inference. There's going to be a trade-off. Like for some people, they're going to want a lot more customizability and a lot more, parameters or whatever. But for a lot of people, they're not going to need that. And for them, this is going to be like super low cost, like high throughput, low latency inference. I think that's pretty cool. Like I hope to see a lot more of that.
Cool. I guess moving on to some audience questions. There are some questions that are very specific to some companies. I think I'll probably skip them. And you can feel free to ask offline. I'll pick the one that's applicable to everybody. And I guess, the last question I think folks been asking is, you got all the big boys, the cloud providers, all adding inferences, and NVIDIA has just announced their own microservices and their products in the mix. So there's no shortage of big boys running games as well. And big fish, I guess you can call them. And then we have us as small fishes. What do you think is, I think the question specifically is like, how does pure play private startups add value for customers here? Given there's so many other players are in this. I don't have any color to add beyond what we talked about, but yeah, throwing it out there. Anyone want to pick it up to see what is the most valuable thing here?
I'll bite like super quick comment. Like I feel like, when you're talking about the big cloud providers, like I love what, the tools, the infrastructure they give us and able to, build things, but they have never delivered on developer experience. And I always like think, to me, I'm biased because like, my startup is focused on developer experience, but I think often that's like the main differentiator. And I think also kind of adjacent to that, like I think there's sort of classic wars of like Redshift versus Snowflake. You could argue like, AWS had Redshift, so they should have won, but in the end, like Snowflake kind of won. Like, I don't necessarily know if like, I think a lot of these like cloud providers, like they're gonna try to juice their margins by going higher up in the stack and throwing some like, services on top. That's good, but as a starting point, they'll make some money. But in the long run, I tend to feel like, the general story here has been, specialized companies focused on, better developer experience, better user experience. Like in general, higher up in the stack, like they have a, they have what it takes to win over the cloud vendors in the long run.
Yeah. Any thoughts? Maybe Dima, I know you're in this space.
Yeah, I mean, but I feel like Erik stole this thoughts from my tongue. But yeah, I think like the data space, like Databricks and Snowflake, following the same logic, should never have succeeded, right? So that's kind of like proof by existence. But yeah, I think it's basically the matter of like listening to customers and focusing on particular, on their particular needs as a primary objective of the company versus, being yet another thing out of like many things which, cloud providers needs to be doing. And I think that shows fundamentally in, ability to customize developer experience or even like some of the optimizations, so far it has been not as exciting. And to be fair, I mean, like some, I think like all of us here like also, use big cloud providers also as their, as a customer. So, from their perspective, there's not as much focus on like higher level services, because actual hosting and like low level machine stuff is still like many of the companies in the space kind of focus on. So from the perspective of cloud providers, it's not existential, right? It's also a win-win if the best developer experience succeed. And I think that was one of the primary reasons why like Snowflake and Databricks were also successful, because effectively it's like competitive advantage from economics if you think about it.
So actually, we get more questions actually directly. So maybe I'll direct one of them. So Erik, you just got one. I know, so you see the Q&A. Basically, the question about like hardware takes 3 to 4 years to get into production. Do you still think it makes sense to have a dedicated LLM transformers hardware? And whatever world moves on to new gen architecture, whatever, whatever new thing is coming out, do you think the risk is high or low?
I am not
What
a
do you think,
hardware
Dallas?
person, so like I'm probably not the right person to answer. But I think there's a point, right? Like I get that like hardware will probably be a little bit behind. Software is always a way to like get the latest models out quickly. But that being said, if hardware is good enough for a lot of use cases, like it might still, just be like so cost competitive that it's still going to win over a lot of use cases, is my expectation.
Yeah, I mean, I can answer that from like previous, like seeing this drama from like PyTorch side earlier on. I think like I mean, it really depends where like how much added value from like research and architecture changes will come, because I mean, if you remember, there was like a previous wave of custom chips for image tasks, like circa maybe like 2015, 2016. There were like 40 companies trying to build custom chips when like ImageNet revolution happened. I think only a handful are still around and kind of all pivoted. I think Grok actually also started originally focusing on like image models. And yeah, they all kind of ran into the problem, like by the time chips got taped out, the leading approaches and leading models kind of moved on. And you end up with this chip which can run VGG really well, but nobody cares about running VGG anymore. So whether it will happen for, LLMs, or like current kind of transformer paradigm is to be seen, because on one side there is some stabilization in like transformer architectures and kind of applying across domains, so maybe it will work this time. On the other hand, it's really hard to predict, what will lead gains, and maybe like one weird trick which was not baked in hardware but it's actually easy to implement on like GPU ends up being crucial, and all the like biggest models investment go there. So it's really like a speed of iteration timeline, like a research question, which makes it somewhat unpredictable. But we'll see. And yeah, as GPU providers like to repeat that also it's a fast moving lunch. So yeah, GPUs also become better and more specialized is like stuff like Tensor Cores or kind of equivalents of that in AMD and stuff. So
yeah. So how you're in the research side, so what do you think about, because I think part of the hardware question is also like, how ready is when the next gen architecture will actually be, prime time? What are you seeing on your side,
Yeah, I think I still want to bring up that video generating thing. Like if that thing happens, I feel there's a great chance that transformer can be replaced, because apparently video data are very dense and the signals are very sparse, and you don't need full attention, right? From a high level intuition. And like I said, if you do video generation, your contact lens start with 1 million, and the attention, like full attention, just cannot scale, whatever hardware you use. Yeah. In essence, I would predict that, like if video generation takes off, like if someone builds a really good model and the community start looking at that, I feel there's a chance, yeah, transformer can be replaced. Yeah.
Any thoughts, Daniel? You're
Sorry.
muted on.
Sorry. I guess yeah, I mean, I know that when you do long context windows, obviously you can do like strided attention and things, and when you look at kind of the whisper architecture and everything, you obviously with long audio sequences don't try and have the entire attention across the entire sequence. And I assume that Sora, the minute-long video, is not it's not like every single frame there is like one massive unrolled quadratic attention. So yeah, I guess the kind of general work that's been done on making attention more efficient in general will keep going. But I guess the one paradigm that will remain the same is, because obviously there's like MLP mixer, and there's all kinds of like interesting architectures in the last few years that have done very well on computer vision tasks and so on, that really took a step away from CNNs. The basic overarching story is remove inductive bias from the network. And if you have enough data and compute, inductive bias is often more destructive than it is constructive. So whether or not it's the transformer exactly, I reckon it's going to be a pretty general architecture, and you know, map models are going to be pretty important in it. Map model is still the biggest heavy computation part of the transformer anyway. So I guess if you have, I don't know, I guess obviously the architectures might be different, and there might be some tricks that then some specialized hardware has failed to embed into the ASIC. But I guess if you kind of strive for optimizing for making map models really, really fast, then you're probably on a good path. But again, I'm by no means a hardware expert, so this is just my own musings. But yeah.
Yeah, that basically saying like NVIDIA still has a big model because their map model is probably the best. Yeah.
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 No, I agree.
Yeah. Got it. Okay. Well, I think one last question I just want to bring in an audience. One question people were asking is, what are the biggest challenges that you find your customers are facing in production? And I think that's kind of like also interesting question, because it seems like all of you have different kinds of customers. My assumption is that. What are the things you think they are having the biggest challenge when actually using LLM production, and how you think they are looking to solve some of these problems? So, Daniel, you want to start?
Yeah, sure. So, I mean, in our case, I think that the customers that really work well with us are people that are a bit overwhelmed trying to keep up with all of the different models, are not able to know which model is the best for their data and their task, even whether that be starting out and just using the foundation model without fine tuning, or knowing which is the best starting point for doing fine tuning in the case of open source models. So I think that, I mean, my feeling with a lot of the kind of bigger enterprises we're talking to is that they're not necessarily fully in the deployment cycle yet. There's still a lot of experimenting, playing around. Like, there's not that many that I can, from what I see, that have that are spending, you know, millions or tens of millions on deployment every year. There's a lot of kind of still exploration to work out how Gen AI is really going to revolutionize the business, and therefore still a lot of research. And I think, yeah, I mean, the thing that obviously for us, the biggest problem that we address is the fact that they don't need to create lots of different accounts with lots of different providers. They don't need to keep up to date with all of the models and the costs and the runtime, and they can get all of that kind of objectively in one place. And that's why they kind of like using what we've got. But I guess, yeah, as you say, everyone's going to be solving different pain points, but this is the main pain point. And the other one is just that the other one is just that a lot of people are just using GPT-4 off the shelf because it's kind of the best model. And particularly when you're building an MVP, like we talked to a few kind of early to mid-stage companies, and when they're building out their MVP, they just want to make sure they've got the best model. So they use GPT-4. Quickly, it starts to scale in a way that they can't control, that they can't manage, because it's $30 per million tokens. And then they want to keep the same performance for the app, but reduce the costs. And that's where the kind of routing angle is helpful. But yeah, these are kind of some of my thoughts on that.
Cool. Hey, Dima, what do you think?
Yeah, I mean, definitely seen similar things to what Daniel mentioned about like some of the companies being like more in MVP prototyping stage, where they often reach out to the biggest model, and then they come to like, okay, now we did the math, and like we need to figure out how to solve it with a smaller model or more efficiency, or like our product experience requires to run it, you know, much faster under like whatever, some latency constraint, and GPT-4 is not going to cut it. So there's definitely that. There's also a lot of, I say, like interest in like kind of guardrailing and controlling what models can do. There were, especially for like, I think that's like a concern for, especially for like more kind of bigger traditional businesses, because there were a few high-profile failure cases, isn't like these like Air Canada or like some like car dealership, you know, like where customer support bots like hallucinate something and it ends up being legally binding according to courts. So there are basically concerns with that. So yeah, all that we talk about kind of guardrailing structure, etc., is I think it's top of mind for a lot of cases. Yeah, I mean, I think on more kind of cutting edge, like startup customers, and like people who try to be on like technological cutting edge, is like, yeah, there are just creative ways of putting multiple models together across modalities, and like what is the best mix, and what is the best way to assemble this. So problems like, okay, how can I hack? How can I kind of be flexible with that? It's also like trend which you see more from like kind of early stage like startup companies.
What do you think, Erik? What is all your customers running into?
I mean, this is obviously filtered by like the customers I talk to who come to us for sort of, you know, skewed reasons, but I think it's like very different. When I talk to smaller customers, like earlier stage startups, it's like they have some like super cool model or whatever, and their problem is like, we don't want to deal with all the infrastructure nonsense. Like we just want to get this out. Like we want to, you know, figure out how to scale this, right? Like we want to deploy this. We don't want to spend too much money. We don't want to deal with Kubernetes or whatever. We just want to get this out. So that's something I think we can serve really well, you know, for those users. I think for enterprise customers, it's a very different type of conversation. It's often more around like, yeah, we're doing some like research. We don't really know how Gen AI could be useful. Kind of like what Daniel said, like we're still trying to figure it out. And I think that's the truth. It's like a lot of these companies, like they're still going to have to figure it out. It reminds me a lot of, you know, mobile or whatever, like, you know, all these like, you know, big companies, they rush to build a mobile app, but then they realize actually this mobile app is not that good. Like we should, you know, what is actually the use case? And it took like a year or two until they actually like caught up to that. And I think it's gonna be a little bit of like trial and error until they actually have like good stuff that's like, you know, customers benefit from.
Hey, Hao, but I'm sure you're talking to customers too now. Whatever you're hearing.
I probably cannot answer this question. Yeah, I will skip. Yeah, sorry.
No problem. No problem.
Yeah.
Cool. So I think that's all the questions. I don't want to keep people hanging here. I'm sure there's going to be a lot of different thoughts. I mean, we didn't even we talked about next gen architecture, but somebody like, no, tell me state space, right? Tell me bases. We can even go that far, but I think we'll conclude here to give people back their time, and I'll give it back to Naomi.
Thank you, Tim. Let me move myself back on the screen. Lovely. All right, great panel. Okay, thank you so much, everyone, for joining our event this quarter. Hopefully you learned something new. We'll definitely be sending a follow-up email to everyone with the recording, as well as a feedback survey where we'd love to hear what you thought of the event, what we can do better next time, topics you'd like to hear us cover in the future. I'm also dropping the link to that in chat, just in case you rather do it now than later. But overall, we really appreciate you joining us. We are planning on doing a lot more of these in the future, and we hope you have a great rest of your day. Goodbye for now.
Bye.
Bye, guys. Bye-bye.